Hey, it's Modern Atelier, and today we are continuing our series about graph algorithms in Rust. We will take a look at breadth first search, and we will have a little demo that will use an advent of code task to showcase this algorithm. So let's get started. In general, there are two ways to traverse a graph. If you have no additional conditions, no additional information, and you are searching for something, or perhaps you just want to enumerate all the vertices of a graph for some reason. One strategy is called breadth first search, and that's the one we will be exploring in this video. The basic idea is that we start from some vertex and then we examine all neighbors of that vertex before examining neighbors of those neighbors and so forth. Another strategy is called depth first search, where instead of checking neighbors of some particular vertex first and then their neighbors, we enumerate paths. So we go from this vertex deeper and deeper until we hit the wall and we backtrack and then we go and look at some other path. But that's not what we will be talking about today. Those algorithms are both very widely used and are basis for many other more complex algorithms. So there is no specific order in which they typically taught. I just decided to take breadth first search first. The algorithm we will be talking about today was invented by Konrad Zuse in 1945 and first published in 1972. But because it was published so late, Edward F. Moore also reinvented it in 1959. We start with this example graph. Let's see how the algorithm works. Apart from the graph, we will also need to have a queue, a data structure that has a property of first in, first out. So essentially, when you put a vertex into the queue, if this vertex was put there first, it will leave the queue first. If it was put there second, it will leave the queue second, etc. Contrast it with stack, another common data structure that we used in our previous video for topological sorting, for example. And we will also need a way to record which vertices were already seen by us. We can use hash set, or we can use any other kind of data structure that will be appropriate for our particular use case for that. Let's start with the vertex A and let's search for the vertex F. At the first step of the algorithm, we always put the starting vertex into the queue and into the scene set. Then we start a loop where we pop a vertex from the queue. In this case, it will be A, and then we check all the neighbors, all the vertices we can reach by an edge from A directly. In this case, we have three of those, B, C, and D. For each of those, we will do the following. We will add them into the queue and into the scene set. Now we are done with A. It doesn't have any more neighbors, so we pop another vertex from the queue. Now it's B, one of the neighbors of A. We now repeat the same operation with it. We look at all of its neighbors and put them into the queue and into the scene set, as long as they have not been seen. If a neighbor was already seen, we will naturally not add it to the queue anymore. So in this case, we only have one vertex that is a neighbor of B, which is F. We put it into the queue and we put it into the scene set. But F is our goal. In this version of algorithm, we don't yet do anything with F, even if we reach the goal. Of course, you can terminate at this point as well, but we will continue with our examples so you can see how the algorithm works in more detail. Let's take the other vertex from our queue. In this case, it's C, and it only has a neighbor D. D has already been seen, so we don't re-add it to the queue. We are done with C. Now we are taking D out of the queue. It has a neighbor E that has not been seen by us yet, so we add this neighbor to the queue and we add it to the scene set. Finally, we take F out of the queue. That's where the algorithm will terminate, and we can return F, or we can return a path to F. And we will see in a second how we can record paths using this algorithm. BFS has a bunch of properties that make it differ from depth first search or other search strategies. One is that it examines vertices in the order of depth from the start vertex. How many edges you need to traverse to reach some vertex from the start vertex. This is what you can call a depth in this context. It also guarantees to find the shortest path to the target vertex as long as this path exists and as long as the path length is measured in the number of traversed edges. In many cases, it allows you to stop searching at a particular depth, and this is important because this algorithm is often used with what is called implicit graphs. Both BFS and DFS can be used to find connected components in a graph. It's also based for many other graph algorithms. Remember our abstract data type approach for talking about graphs? There are multiple possible representations of graphs. So, depending on the particular algorithm that we are trying to apply, we need to have different methods that we can use on the graph. In our case, we only care about graph being able to return us adjacent node of some particular node. And adjacent are nodes that you can directly reach from some node via an edge. In this case, we are returning a vector of nodes. Naturally, this is not required. In Rust, you can also return an iterator. It can be some other kind of collection or data structure. So it really depends on your implementation, but being an abstract data type, we don't care about such details. I just introduced a bit of terminologies that we did not cover yet: explicit and implicit graphs. What does it mean? Well, explicit graph is a graph that you store directly as a data structure. You store vertices and edges and some attributes that they might have in some data structure in computer memory or on disk. This is called an explicit graph, and we've seen already two kinds of representations for those. One is our index graph representation, where we use vertex indexes to save space and avoid storing vertices multiple times. And another one was the representation we used in topological sorting video, where we use a hash map directly, and we don't have any additional metadata associated with the other edges or vertices. Naturally, there are many more possible representations of explicit graphs, and the one you choose depends primarily on your use case. Now, implicit graphs are not stored directly in computer memory. Instead, you usually have some state, and you have some functions that allow you to work with this state like a graph without creating all the vertices and edges connecting those vertices and storing them somewhere. In our example task, we will see that we will have coordinates, positions, and just using this position with x and y coordinate, we can create an iterator over adjacent cells. So that is one of the cases of having an implicit graph. And now to our demo and an example implementation of breadth first search in Rust. We will use Event of Code 2016 day 13 part 1 as our demo case. I will skip reading you the whole task instruction, but in short, this is what it requires. You're given a constant n and a cell at coordinates x and y. For that cell, you can determine if this cell is an open space or a wall. The n number essentially describes a maze, which is pretty cool because you just use one number to represent a whole graph in this case. And that's why we use implicit graph representation here, because we don't actually need to compute all of the graph. It also allows you to create an infinite size graph, naturally. We have this mathematical expression that we compute, and then we convert it to binary, and we count the number of bits that are set to 1. If it's odd, then we have a wall, otherwise it's in an empty space. The task is to find the minimal number of steps to reach a cell at coordinates 31, 39 from a cell at coordinates 1, 1, given the number n and given that you can only move up, down, left, and right. First, we will start with describing our position structure, which will only have x and y as unsigned 32-bit integers. And then we can implement two helper methods. One, this formula and logic for checking if we have a wall or an empty space, which is called isOpen, and naturally it returns a boolean, and a function that returns us iterator over adjacent cells. Since we cannot move diagonally, the easiest way to produce such an iterator is to create a constant array, adjacent delta, in which we will have tuples for increments, essentially, for our x and y coordinates. And you can imagine going left will be x minus 1, going right x plus 1, going up will be y minus 1, going down will be y plus 1. Naturally, we use screen coordinates here, so y axis goes down. Given this array, we can then iterate through that and essentially compute all the coordinates that are valid. And for us, valid coordinates will mean that they are non-negative in this case. So we can use handy checked at signed function from the standard library. Our BFS implementation will take the magical number n, the start and goal positions, and will return us a hash map mapping position to position. This hash map will be used to reconstruct a path from start to goal, and we will see how in a second. But let's for now just initialize it and call it parents. Then we create our queue. To represent a queue in Rust, we typically use vec-dec collection, and we immediately put start vertex there, and we also create the scene hash set, and also we put start there. As long as we have elements in our queue, we pop them out of the front of the queue. If the current element we are examining is our goal, we return the hash map of parents. If not, we iterate through all of the neighbors of the current vertex. In this case, it will be adjacent cells as long as those cells are not false. For each of those, if scene does not contain the next vertex yet, we put it into the scene hash set. We then push the next vertex in the end of our queue, and we insert an entry in our parents hash map. We say that we arrived into the next vertex from the current vertex. Since we will visit each vertex only once, it means that we will be able to reconstruct the shortest path to each vertex that we will reach from the start using this hash map. In the end, once we ran out of the elements in a queue, or in case we found our goal, we return parents. How do we reconstruct the path? For that, we use the parents hash map, and we select the vertex for which we can reconstruct the path. In our case, it's goal, and we will return our path as a vector of positions. We will not include goal into the path. We start by initializing path as an empty vector. We set our current vertex to be our goal vertex. And then as long as we have a parent, we will take a parent of the current vertex, push it into the path, and set the current vertex to be the parent. In the end, we reverse the path vector that we got and we return it. This way, we can get the path to the goal. This is sufficient to solve the task. So this is solution for part 1. We take the magical numbers, the start and goal positions, and we return an option of the usize, which in this case will be path length. We construct the parents hash map with our BFS function. We reconstruct the path to goal with the reconstruct path function. And then as long as it's non-zero, we return the length of that path. And I also wrote a test that verifies that both the test assignment works and that our solution also works. Naturally, I used Advent of Code website to make sure that I solved the task correctly. And now it's time for the demo. I used egui library to create a demo for this task, and I will have a video about this library shortly, hopefully. You can see that you can change the number you get, and you can also change the amount of levels we draw. And then we can play an animation to show a solution. Now, the cool part, we can also use the slider to move stuff around. You can see that apart from the path, we are also showing other vertices from our scene set at the same depth as path. And you can, of course, check out the repository with this code to figure out how it was done. And as usual, link for that will be in the description. And here you can really see the behavior of breadth first search, I feel, especially when you arrive at this place. Here, you can see that we had those 3 neighbors at the same depth, and then we have those ones selected as well. It looks really like water filling in this maze, and that's also a good analogy to have. Breadth first search can also be used to implement flat fill algorithm. It's not the most efficient way to do it, but it is a workable way. And that's it. This algorithm is both delightfully simple and very useful. If you want to have a bit more fun with breadth first search, I recommend solving the second part of the Advent of Code task. You also can find the solution in the repository linked, and apart from the code that I wrote for this particular Advent of Code task, it also contains a generic implementation of breadth first search for our index graph representation. I will also link it. And I have a bit of a good news. I got my first GitHub sponsor. Thank you so much, Muchin. Arigatou gozaimasu. Of course, if you want to support me doing those videos, please leave a like and subscribe. And if you can, please become my sponsor. Each one helps. Thank you very much for watching.